We will now move away from the Earth and start talking about escape velocity, the velocity you need to escape the Earth's gravitational field. Before we do that, we're going to have to expand our definition of gravitational potential energy. We've been using gravitational potential energy equals mgh. However, that only works near the surface of the Earth or whatever planet you're dealing with. Once you start getting further away from the center of the object, we cannot use mgh. So let's see why. Little g, or the gravitational acceleration, is equal to big G, the universal gravitational constant, times the mass of the planet that we're talking about, or celestial object, divided by the radius squared of that object. As the object's height above the surface of the planet increases, the distance from the center of the planet to that object is not just the radius of the planet anymore. We have to add in how far away it is from the surface. Now, mgh worked because really, no matter how high you can walk on Earth, the radius of the Earth is always going to be much, much greater than whatever distance you are above the surface. Sure, there's minor corrections from Mount Everest, etc., but it's really the same value of g wherever you go. So we have to derive a more general expression to find this gravitational attraction. So we're going to use Newton's universal gravitational force equation, where the force is equal to basically little g here times the mass of the object that you're interested in. And this r, this is not just the radius of the planet anymore, it's the distance from the center of the planet to the object. So take a little time on this slide. This is a very important piece to start with. Mathematically, we've gone about as far as we can now, given the fact that most of you haven't taken calculus, because to derive a more general formula for the potential energy of this object requires calculus. The gravitational force is not constant. It keeps decreasing as you get further away. Hence, there must be an integration technique used to solve for the potential energy. So we'll just present the result here, and for those of you going on to APC, you can cover it then, and it'll be quite cool. And we're also going to use a more common physics term for the gravitational potential energy, capital U sub g. Capital U is normally used for potential energy at the higher level physics courses. And what we will find out is that the potential energy due to gravity is equal to a negative big G universal gravitational constant times the mass of the object, the large object, the planet or the celestial body, times little m, which is the mass of your object that's moving away, divided by r, where r is the distance between the center of mass of the large object and the center of mass of the small one, which normally is not terribly important. The center of mass of the small object is not that far away from its outside. Now, what do you think the negative sign in this expression means? When the integral is solved, an assumption is made that the gravitational potential energy between two objects that are an infinite distance apart is zero. Now, when we add that assumption to the fact that gravity is always an attractive force, the negative sign pops up both in the math that we do and also the concept that we want to get across. Now, how can we reconcile this negative sign with the fact that we normally think of gravitational potential energy as a positive number? You have to go back and think of what GPE, or U as we now call it, really means. The gravitational potential energy measured for objects near the surface of the Earth is really mg h minus h0, and h0 is normally set to 0. That's the ground. So it's really the change in height above the Earth's surface that is important. GPE is not an absolute number. Let's look at this graph here. This is a potential energy, gravitational potential energy. This is how far you are away from the center of the Earth. And it's minus gmm over r. So that's a curve like this. It's a 1 over r curve, but it has a negative in front of it, so it's flipped. So let's just take 2 points, and we'll just put some arbitrary numbers here. At this point here, let's say you're 1 unit away from the Earth's surface, and this point here, let's say you're 2 units. The energy down here when you're very close to the Earth's surface. Let's call that -4, for example. And up here, you can see how, let's call that -2. So now, when I use this formula here, h minus h0, I get -2 minus a -4, which will give me a +2. So there you go. There's our positive gravitational potential energy when you're above the Earth's surface. So to summarize, as you get further away from the center of the Earth, the potential energy becomes less negative. Therefore, the difference between the final potential energy and the initial potential energy will be positive. Again, MGH will still be a positive number like we've been working with all course.